Okay, moving along to question 6. Adamantane has an empirical formula of C5H8 and a molar mass of 136 grams per mole. What is its molecular formula? So we're going to start by calculating the formula mass of this C5H8 empirical formula, and that's going to be 5 times the mass of carbon plus 8 times the mass of hydrogen. So 5 times 12.011 grams per mole plus 8 times 1.008 grams per mole, and that all adds up to 68.119 grams per mole. So that is the mass of the C5H8 unit. And then the number of those formula units that are in the molecular formula will just be the molar mass of the molecule divided by the mass of that formula unit, 136 grams per mole, divided by 68.119 grams per mole, which is 1.99651, and that's very, very close to 2. That tells us that the molecular formula has 2 of these formula units, and so the molecular formula is 2 of the C5H8, or in other words, C10H16. And that's our molecular formula for adamantane. Okay, next question. Oxalic acid contains 26.7% carbon and 2.2% hydrogen by mass. The remaining mass is oxygen, and we want to find the empirical formula for this compound. So first off, I'm going to find the percent mass of oxygen, and that's going to be 100% minus the 26.7% carbon minus 2.2% hydrogen, and so that works out to be 71.1% oxygen, or in other words, 71.1 grams out of every 100 grams of compound is oxygen. And so this means that if we had 100 grams of our compound, it would contain 26.7 grams of carbon, 2.2 grams of hydrogen, and 71.1 grams of oxygen. Then converting these grams into moles of the 3 elements, 26.7 grams of carbon, to turn that into moles, we put in the atomic mass of carbon, 12.011 grams is 1 mole. The grams cancel, and we find that we have 2.22 moles of carbon in our 100-gram sample. Likewise, we have 2.18 moles of hydrogen and 4.44 moles of oxygen in the 100-gram sample. So these numbers of moles are in a ratio of 2.22 to 2.18 to 4.44. Then if we divide through by the smallest number, which is 2.18, we get 1.02 to 1 to 2.04, which is quite close to 1 to 1 to 2. And so that tells us that the empirical formula is going to be CHO2. So there's the carbon and hydrogen are in a 1-to-1 ratio, and then for each carbon and hydrogen there are 2 oxygens. And that's the empirical formula for oxalic acid. Okay, moving along, question 8. Just as the prefix kilo represents a multiplier of 10 to the third, the prefix zepto represents a multiplier of 10 to the minus 21. And we want to know, A, what is the mass in grams of 1.00 zeptomoles of vanadium? And B, how many atoms are present in 1.00 zeptomoles of vanadium? And we're given that the Avogadro constant is 6.022 times 10 to the 23rd per mole. Okay, so for part A, we want to know the mass of 1.00 zeptomoles of vanadium. So a zeptomole, based on the information that we were given, the zepto prefix means 10 to the minus 21. And so 1 zeptomole is 10 to the minus 21 moles. And so in order to find the mass in grams of this amount, we first need to convert into moles. So 1.00 zeptomoles, to convert that from zeptomoles to moles, we use the relationship that 1 zeptomole is 10 to the minus 21 moles. Zeptomoles cancel. And then if we want to convert from moles to grams, 1 mole of vanadium has a mass of 50.942 grams. We just read that off of the periodic table. And then moles cancel. And when we multiply this out, we find that the mass is 5.0942 times 10 to the minus 20 grams. And then we, rounding this off, our 1.00 has 3 significant figures. The 50.942 has 5 significant figures. All the other numbers are exact. So we're going to go with the lesser of those two precisions, 3 significant figures. And so we'll round off our answer to 5.09 times 10 to the minus 20 grams. Okay, and then in part B, we want to figure out how many atoms are present in 1.00 zeptomoles of vanadium. The Avogadro constant tells us that 1 mole of vanadium will contain 6.022 times 10 to the 23rd atoms. And so, now careful, even though we just calculated the number of grams, we don't need that in part B. Part B, we're still looking at 1 zeptomole. So we're not going to do anything else with our answer to part A. Part B is going to be a completely separate problem. We've got 1.00 zeptomoles, and we want to now convert this to atoms. We have a conversion factor from moles to atoms, and so we'll begin by converting from zeptomoles to moles. 1 zeptomole, again, is 10 to the minus 21 moles. And then we want to, then our zeptomoles will cancel. Then we want to convert from moles to atoms. We can use the Avogadro constant. 1 mole is 6.022 times 10 to the 23rd atoms. And so now our moles will cancel. And when we multiply everything together, we get 6.022 times 10 to the second atoms. And again, we want to round this off to an appropriate precision. We've got 3 significant figures here. We've got 4 significant figures here. So we'll round this off to 3 significant figures. And then, so we have 6.02 times 10 squared, or that's equivalent to 602 atoms in a zeptomole. All right. And I think I'm going to stop here and continue in the next video.